Okay, so let's start. So my name is Olivier Monfort. So as you understood, I am not Slovak, I'm French. So this is only to highlight that Slovakia is also attractive for other people that's going out of Slovakia. Okay. So I already did my name. So I'm researchers at Faculty of Natural Sciences, faculty where we are making a lot of chemistry, including inorganic chemistry, and I am the group leader of the M2 groups. So today my talk will be on the protection of the water resource, which is an environmental challenge. So what you will learn today? A little bit about my research group, because most of the students doesn't know what we are going to do in Slovakia in this beautiful research group, which is the M2 groups, and also a lot about the importance of the circular economy of water. Basically, we are established for 5 years, and our group is composed of 2 labs. First lab is on materials innovations and advances, which is basically led by Dr. Martin Motola, my colleague, and in these teams, they are dealing with the preparation of innovative materials for energetical applications. The second lab is based on mechanisms and studies in remediation processes. So it's kind of barbaric name, but basically here in this lab we are doing investigation on these innovative materials for some environmental applications, including the water treatment, which is a topic of this lecture. So concerning the group in numbers, so we have published recently during these 5 years 80 publications, which is quite good and quite dynamic for a young research group. We have 5 ongoing national and international projects based on science, but also mobilities. We have an average age of 30 years old. Okay, so Slovakia is also attractive for young scientists. And which is very important, scientific research is made of international collaborations and also international members of our groups, because you can find in our group some Slovaks, some French, Ukrainians, Indians, Pakistani, Chinese, and also recently Iranians. So let's come back now to the core of this presentation. So what is the circular economy of water and how it is linked to the water treatment, and especially the wastewater treatment. So why first saving water? This might appear as a stupid question, I know, but let's look at the numbers. On the planets, on the blue planets, we have only 3% of fresh water. From this 3%, less than 1% is accessible. You should add to this that this less than 1% accessible water is devoted to the agricultural and industrial sectors, from 80 to 90%, which is huge, but logical, because you should feed the population of the planet, and you should make some progress in the technologies. So that's why. These numbers are quite depending on the countries, of course, and the seasons. To this number, you should add issues related to the water shortage. Okay, on the planet we are more and more, and the climate is, let's say now, crazy. We are facing to more dryness, more intense dryness, and longer dryness. So that's why it is important to find efficient treatments of this water. Why? As you might know, the treated wastewater is released in the environment, okay? And a lot of this water is lost, basically. So why not to reuse this treated wastewater in the circular economy? So for example, we can potentially reuse this treated wastewater in the agricultural irrigations, which is consuming a lot of water. And also, why not one day to drink the treated wastewater? So we'll make a small poll in the audience. Who is willing one day to drink the treated wastewater from his or her toilets? Raise your hand. Okay, 1. That's it? 2. Okay. I know it might appear disgusting, but it is the future if we want to save the water on the planet. Okay? So in numbers, when you look the circular economy in numbers, so I am French, so I will give some numbers from France. Recently, a big scientific plan has been set in France, because less than 1% currently is used in the circular economy. And our presidents want to reach 10% of reusing treated wastewater by the end of 2030. Why this plan? Because, as I told you, the water resource is more and more rare. And in France, we have issues related to the level of water underground, but also on the surface. Okay, so rivers and so on. So that's why it is important to potentially reuse the treated wastewater. This number might appear funny because when you look other countries, Italy, Spain, they are already reusing 10% of the treated wastewater. Why? Do you have an idea why? It might be obvious. These countries are located southern than France, so they are facing to already intense and longer dryness. Top example of countries that are reusing wastewater is Israel. In Israel, they are reusing more than 80% of the treated wastewater. And this highlights the fact that it's possible because I don't know if you know people from Israel, but they do not have 5 hands, two heads, and so on. So basically, it is feasible. In Slovakia, so far you are also reusing not so much of the treated wastewater, but the simple fact is, and you are lucky for that, well, we are lucky because also I'm living here now, we have the so-called jedinečného, so it is a big reservoir of fresh water. So that's why so far you are not facing these issues, but in the future you and we might to find some alternative. In terms of numbers, I will give you a last number about the circular economy. In the European Union, if we want to valorize the treated wastewater, we can save about 6 billion of cubic meters of water. To get a better image of these numbers, it is 3 times the Balaton Lake. So now when you will go to surf or to make some swimming at the Balaton Lake, you can tell your family or friends that you see, if we were saving the treated wastewater, we could save 3 times the Balaton Lake. Okay. In terms of Olympic pool, is 2,500 swimming pool, Olympic swimming pool. So, to see if it is feasible, the circular economy of water, let's look about how treated of water or wastewater are treated. So this slide looks complicated. I just wanted to highlight that basically wastewater are treated by a combination of different processes. Physical processes, biological processes, and chemical processes. All these processes have their own advantages and disadvantages. For example, physical processes, they are efficient, but they only move the pollution from one phase, so from the water to another phase, the solid adsorbent, for example. Okay, so we do not treat the problem of the pollution, but it is efficient to make the water cleaner. Then biological treatments are good in the sense that they are very cheap, but they take a long time to implement because you need several weeks to make your biological treatments. And the second disadvantage is that biological treatments can only degrade biodegradable compound. And then you have chemical treatments. Chemical treatments are very efficient, but you should use chemicals, so it is also disadvantages. But anyway, so far the conventional wastewater treatments are quite efficient because of the combination of these processes. Also, what I want to highlight in this slide is it is according to the type of wastewater, you will have a different treatment compared to other wastewater origin. For example, you have wastewater from municipalities, wastewater from industries, and you have a lot of several industries, wastewaters of whatever industries or agricultural sectors that use water and need to treat it. Also, the treatment of water depends on the purpose. Okay, here we are talking about wastewater, but also you can make the treatment of water that you will drink, and this is also again a different treatment. So far, how efficient are the wastewater treatment plants? So these numbers are quite interesting because it comes from recent publications, which was published in PNAS. It's a good journal in 2022. And they make a survey of the pollution, the pharmaceutical pollution, which is nowadays called as emerging pollution, in all the rivers all around the world. Okay, so I put the number of concerning Bratislava, especially from the Danubes, the little Danubes, and treated effluent from wastewater treatment plants. And some number about Paris, because you understood I'm French. So when you look the numbers, so you can still see that there is some pollution, okay? So it means even if it is in nanogram per liters, which is quite good in terms of values, because comparing other regions of the world, this value is excellent because we are in the European Union, okay? But what I want to highlight here is that if the wastewater treatment plants are not 100% efficient, you can have accumulation of the pollution and you will have an increase of these numbers, okay? Also, another information from this table is that one of the top pollutants all around the world is metformin. It is pharmaceutical, and do you know for which disease? Or I will give you the question in another way. What do you think what is the most spread disease in the humanity? Any idea? Diabetes, so cukrovka in Slovak. So that's why you have metformin as a top pollutant. Then when you look France, you have a lot of nicotine and paracetamol for two reasons. In France, we are smoking a lot comparing to Slovakia. And today was a good example because I wanted to smoke, but nobody has a fire to give me. And paracetamol, because in France we have one of the best, and I think the best health insurance, so all the medicines are for free basically. And paracetamol is one of the most used medicine in France. When you look Bratislava, gabapentin is an antileptic, so might signify that maybe we have a lot of epileptic guys in Slovakia, maybe. And caffeine, and I will highlight this caffeine because it is a compound that I attempt to degrade using innovative processes in my research group. And caffeine has two origins. First, from excretion, okay? When you drink a lot of coffee, not all is metabolized by the body, so you can find caffeine in the excretion, okay? When you go to the toilets, so think about caffeine, don't drink too much coffee, okay? Also, when you make coffee, the residue that you do not consume, do not put in the sink. First of all, you will destroy the tubes of your kitchen, but also you will produce some pollution. So again, when you will think about making coffee, think about the pollution you will create. So do not throw the caffeine residue in the sink. Also, a funny fact of these numbers is at that time it was done where I would say I'm living in Vracunia, so you know what I want to say now. It was at the time that in Vracunia you have a lot of narcomans, okay? You know why? What is the most famous building in Vracunia? Pentagon. Now it's totally safe place. I'm living there, next to Pentagon, 50 meters. It's totally safe, but at the time of the measurements, the situation was worse there. And why caffeine then? So caffeine for drug consumer, it is used to cut heroin and cocaine. So if you are a drug consumer, please make sure that the product is pure, okay? Because then it will create some caffeine pollution. Of course, in the world, caffeine is top 3 pollutants because the caffeine consumption is quite huge all around the world. So that's why caffeine is a kind of very important emerging pollutant. Okay, so now is there some alternative to these conventional treatments? So recently, the European Union has released some directive about the water quality. So now the limits of the pollution is decreased, which is good for our health. But in terms of wastewater treatment, it means that we should find more efficient treatments. So how to make our water great again? So I'm not telling them because of Donald Trump. It's because also in France we have a huge scientific program which is called Make Our Planet Great Again. Okay, so it is a good motto. So how to make our water great again? You have 3 possibilities. Either find new technologies, either improving existing technologies, it is what it is currently doing, and how to potentially integrate already known technologies in the conventional treatments. And it is what I would say that we are trying to do at fundamental stage. Okay, we are fundamental science research group in the Department of Inorganic Chemistry. So how it is possible to integrate now technology? So I don't know if you are familiar with chemistry, so I will not enter too much details, but this slide is only to show that there is a process which is not for a couple of decades, which is called advanced oxidation processes, where you produce or generate some inorganic radicals like hydroxyl radicals. It is highly oxidative, highly reactive, and highly efficient in the destruction of the organic pollution. So if you want to know more about how it is acting, just look the last equation. So basically, whatever pollutant you have with hydroxyl radicals, after a couple of minutes, you can degrade the pollutants completely into full mineralizations. So it means CO2, H2O, and some inorganic compounds like sulfates, nitrates, and so on, which are much more less toxic compounds than the organic pollution. And in our group, we are trying to do these advanced oxidation processes, but using sustainable energy, meaning the use of solar light. And how? Basically, we are preparing nanomaterials which are photoactive. What does it mean? It means that under solar light, in the presence of these materials, we can produce these hydroxyl radicals that are the let's say the main reactive species in the degradation of organic pollution. So we are preparing material in form of nanopowders, nanotubes, and nanofilm. Then how we try to apply these materials? As I told you, we are a fundamental research group, so we are making experiments at lab scale. And first we are inserting these nanomaterials in some pure water that where we make some artificial pollution with, for example, caffeine. Okay. Here you can see on the picture one of our reactors, and then what we are trying to do is not only to see the efficiency of these materials, but also how the degradation is occurring, because if you doesn't know how the material is acting, you cannot understand it, and if you doesn't understand it, it is hard to apply one day. Okay. So basically, we'll make a lot of investigation about the mechanism of degradation of these pollutants in presence of these nanomaterials and simulated solar light, because these photoreactors are simulating solar light. Okay, especially this one, the UV part of the solar light. So in the research group, we are also making other research directions. For example, production of hydrogen. You know that hydrogen is considered as the green and future fuel of the planet, and also fuel cell to make some production of electricity. Okay, so the take-home message, I would say that save water. Okay, it's obvious, but think about this caffeine story. Okay, so every day, every morning or every evening, I don't know when you are drinking coffee, think about the caffeine pollution. Okay, drink a bit less, because caffeine is good because there is a lot of antioxidants, but too much is not so good, neither for your health and the health of the planet. And the second take-home message is the drinking wastewater or treated wastewater would hopefully, or unfortunately for some of you, feasible because of the circular economy. Circular economy of water is the future. Okay, so that's it for me today. Just want to say that we are looking for some students which are interested in these thematics, environmental thematics, either in bachelor, master, or PhD studies. So you are welcome. You can drop me a message or look on our website. You can scan this QR code. And thank you for your attention. If you have some questions in English or in Slovak or in French, it's okay. Thank you. Okay, I'm good in time. Whoa, no question? Okay.
Thank you for the presentation. So I wanted to ask, so when you see there are different kinds of pollutants, like 3 of them in Slovakia and 3 of them in France, so how do you degrade taking one material or is it multi-materials, like few of them together and then you try to see their degradation?
Yeah, I get your question. Thank you. The table I show, it's not the only pollutant that is found in Slovakia. It's overview of some top pollutants. Then concerning your question about the degradation of, if I understood well, the selective degradation of some pollutants, since we have these advanced oxidation processes, the reactivity of radicals are non-selective. So basically, the radicals will destroy everything they will find on their way. So either good organic molecule, like natural organic matter. Natural organic matter is very important for the fertility of the soil, for example. But unfortunately, you will destroy also that. So then when you will treat this water, it will be good to make some biological process or biocompatible process to make the water, let's say, better for the environment. Because pure water, it will not damage the environment, but it will be not useful for the environment. And these hydroxyl radicals can be triggered whatever the material you used. The most important is to design the materials very well. Either I was boring or you are tired. Yeah, that is a good question. Actually, using nanomaterials is good in the sense of the efficiency if you look at the pollutants which is targeted. But of course, if you find some nanomaterials in the environment, it is not good at all, okay? Recently, I think European Union also set some limits about TiO2 nanoparticles in foods and so on, or something like that. So nanoparticles is not good in the environment because it could enter the, I'm not a biologist, but it could enter the cells and it might lead to some damages. But anyway, these nanomaterials are used during the treatment process, and of course then after the treatment process you should remove the nanomaterials. And if we compare the different type of nanomaterials, it's better to have supported nanomaterial like nanotubes than nanopowders, because nanopowders are quite hard to separate even if they are magnetic. And the supporting nanomaterials are quite easy to move from the solution. The only difference between these two possibilities is that nanopowders will be much more efficient because you have higher specific surface and they're moving all around the media, and nanotubes or supported films will be non-moving, so you will lose in terms of kinetics, but the efficiency will be the same if you compare at proper time scale. Okay, thank you.